Hey Bengals, this is Miss Timmons here. Today we're going to be talking about the origin of the universe. So just to kind of recap that first clip that you saw of Horton as he's talking to all of the characters in Horton Hears a Who. They're talking about instances where maybe they're encountering things that are actually really small, and maybe on a comparison note they themselves are actually really small, which pertains to what we're talking about today, because in our world there are a lot of things that we can't see because they are too small, like the cells in your skin or germs. You can't see any of those cells because to us they're really small. Well, if you take us and compare our size to the entire universe, we are the small ones that are visually insignificant in the grand scheme of the universe. So we're going to talk about one of the theories as to how the universe began, and we're going to start with the Big Bang. So to understand this theory of the origin of the universe, we have to kind of rewind and go back in time. So all of the galaxies move closer together, and all of the matter in the universe would have been in one single place at that time, and that was billions of years ago. Scientists estimate about 10 to 15 billion years. The universe was really small. It was really hot and it was really dense. And then one day, for some reason, the universe exploded into what astronomers later called the Big Bang. According to this theory, the universe has been expanding ever since this Big Bang, this explosion. And because of this expansion, the universe is a whole lot larger. It's billions of times larger than what it started out as. Now, let's talk for a minute about the idea of this being a theory. We can't really go back in time, in reality, go back in time and figure out whether or not the Big Bang is in fact true. But scientists base this theory on a very large amount of evidence that support some of the portions of this theory. So we're going to talk through some of these pieces of evidence. In question 1 of your essential questions, you do need to list these 4 evidences that we talk about. And I don't want you to just write down what it is. I want you to write down the explanation of this particular piece of evidence. So let's get started. The first piece of evidence that we're going to talk about is the fact that the entire universe, the majority of this is made of the 2 smallest elements on the periodic table, being hydrogen and helium. These elements even exist in empty space. The heavier elements like oxygen, iron, sodium, they only exist in areas where stars have died. And this is significant because the theory is that during the Big Bang, it spread hydrogen and helium throughout the universe, and then as different energies move around, there's a process in stars that begin where you combine 2 hydrogen atoms to make a helium, and then 2 helium atoms to make a beryllium. They basically run into each other, they fuse into each other. It's called nuclear fusion, and make bigger elements. When this happens, it forms a star. So it makes sense to have the bigger elements in areas where only those stars have been, to create those bigger and bigger elements through the process of nuclear fusion. And yet you can still find hydrogen and helium throughout all of the universe. So this is one of the pieces of evidence they use to talk about this. Our second piece of evidence deals with the fact that scientists have noticed what appears to be dark space far away from stars, but it has a temperature. So most of the universe is extremely cold. If you go out into outer space, it is extremely cold. However, there's still a temperature, and that heat had to have originated from somewhere. So it supports the Big Bang Theory in that this heat would have possibly come from the initial explosion of the Big Bang. They've also noticed, as they track the temperature of the universe over the last 100 years, that space is also cooling. Well, if you have, a pot of water on the stove and you turn it off, by the next morning that water is going to be cold because it cools off. So it required a heat source in the beginning, and then after the heat source is gone, over time, that energy will dissipate and the temperature will cool back off. That same concept is how they apply this change of temperature to the Big Bang Theory, that initial explosion, it gave temperature to areas where there isn't any matter, isn't any stars or planets to give temperature, but that temperature is also cooling off. And that's significant because that indicates that a long time ago, that temperature would have had to have been much, much hotter than it is now. So evidence number 3. Evidence number 3 states that radio astronomers, specifically in 1965, were using microwave receivers, which is a type of telescope, and they pointed at the sky and they noticed they were getting microwave radiation from every direction. And what they eventually figured out is that there is microwave radiation everywhere throughout the universe, and even in areas that not only don't have stars now, but have never had stars. Which means, again, that kind of comes back to where does all of this come from? They attribute the origination of that microwave radiation from the original blast of the Big Bang. And then that radiation has just been since expanding and spreading throughout space. So just another piece of evidence that they use to kind of prove and support their theory that everything started from this original explosion. Finally, astronomers have observed over the last several years a few things. Number one, that the vast majority of galaxies that we can observe from Earth are what's called redshifting. What that means is we can tell that they're moving away from Earth. So if many of these galaxies are moving away from us, what that means is that once upon a time, these galaxies were much, much closer to us. So if they rewind time, these galaxies would have theoretically been much closer to our own galaxy, and therefore that kind of supports this idea that the universe is expanding. It's getting bigger because everything is moving away. The other part of that is that they've calculated how fast these galaxies are moving, and that calculation is that many of these galaxies are moving on average of 1.3 million miles per hour. So not only are they moving, but they're moving very fast. Even our own galaxy, the Milky Way galaxy where we live, is moving, and so they're able to kind of base the movement of galaxies compared to our own and determine that they are in fact moving away, and they have to be going somewhere. So the idea is that they're expanding as this universe is expanding. Alright, so let's recap now then our 4 evidences. And granted, on your Wix page, you need to have more detail than this, but this is just a quick summary. So, number 1, everything is made of simple atoms. Everything has been built from these simple atoms, and when I say simple atoms, I'm referring to the hydrogen and helium, and that it's found everywhere through space. Number 2, space is cooling off, and that areas that don't have any stars or galaxies or anything like that have a temperature. Number 3, that there is a lot of radiation throughout space, even in areas that don't have stars now and never have. And then finally, the universe is expanding and it's moving very, very fast. The galaxies are moving very, very fast. So the next thing we're going to be looking at is the methods that are the methods that scientists use to measure distances in space. So to first give you an understanding of why some of these units exist in the first place, I want you to check out this clip. So the question that we have to ask ourselves here is, why light years? So there's two main units that they use to measure distances in space. So the way it began is that originally astronomers began to try and measure the distances between our sun, the planets within our solar system, all of the moons that are around the planets in our solar system, and unfortunately meters was just too small of a unit. So instead of using meters, they used a unit, they created a unit called the astronomical unit. And the astronomical unit, or the AU, is equal to the average distance between the sun and our Earth. So when astronomers wanted to measure distances, though, between the stars and the galaxies, even the astronomical unit became much, much too big, or too small. So they once again had to create a new unit of measure called the light year. So just to kind of give you an idea, a light year, number one, it's the distance light travels in 1 year. So to put that in meters, 1 light year is equal to 9,461 quadrillion meters. That's that big number at the bottom of this screen. So to give you an idea of what that would look like, let's do a little bit of research. So what I'm going to do is so Wolfram Alpha is a kind of a computing search engine, and what I'm going to do is search for a known star that is within our own galaxy. So distance from Earth to Sirius. And Sirius is a star. Kind of give it a second. So I want you to kind of see the distances that it's talking about. It's 8.591 light years from Earth. So if we look at some of the conversions, that's 543,300 astronomical units. So even that number with the astronomical unit was still way too big. You convert that then into meters and kilometers and miles, 50.5 trillion miles. These numbers just got too large to manage, which is why they developed the unit of measure of light years. So again, light year is the distance that light travels in 1 year. So what I want you to do is take a few minutes, and I want you to research the distance. So we researched the distance to Sirius, but I want you to research the distance between Earth and the closest star to us other than the sun. So take some time. That's your action item for this particular Wix, and I'm out. Y'all have a good day.